everyone, and welcome to our second episode of Doing Research in Psychology Advanced. So what do we have on today? Well, we're going to be taking a look at the sorts of claims we make in psychology. So when we can infer causation and when we can't, and why that might be important. Then we're also going to take a look at how we measure relationships and correlations in psychological research. And then finally, we're going to be introducing something a little bit new in signal detection theory. So this, I think, is a really good framework for thinking about hypothesis testing in psychology and how we can apply that thinking more broadly. How do we distinguish between signal or systematic variation and noise or chance or random variation? So it's a framework that we can use to think about all sorts of discriminations we make in our everyday life. To start, let's take a look at when we can and can't make causal claims in research in psychology. Well, this really depends on the kind of research that we're doing. Is it observational? Is it correlational? So are we looking at relationships between things? Or is it experimental? Are we holding things constant and only manipulating or wiggling one thing at a time? And those sorts of elements of research really influence the sort of claims we can make from data using statistics. So let's drill down a bit further and take a look at what causation means in the context of correlational research to begin with. So in correlational research, we're looking at relationships among variables that are observed and measured. So critically, we're not manipulating or changing anything as researchers or experimenters in a correlational study. We're measuring variables as they occur naturally in the world. And just to bring back a term that you may have encountered in the past, but it's a pretty important concept to have in the back of your mind as you're thinking about research designs and questions about research methods in psychology, is this concept of operationalization. This is important in all kinds of research, but in correlational research, this is essentially the process of distilling or defining our variables so that they can be measured. Right? So sometimes we might be looking at or interested in a relationship between, say, exercise and health outcomes. But those are fairly fuzzy concepts. And so in order to understand whether or not there is a relationship there, we need to make decisions about how we're going to measure those variables and what we mean by each of those variables. So operationalization is a really critical process in correlational research. Also in experimental research, but we'll get to that in a second. So what kinds of claims are we talking about when we do correlational research? Well, the kind of things that we might claim from a correlational study are things like X is related to Y, or X correlates with Y, or X and Y tend to go together, or X corresponds with Y, or X predicts Y, or X correlates with Y. X and Y happen to go together. These are the sorts of claims that we can make based on correlational research, right? So it's when things tend to go together is a really good way of thinking about correlation. But you may have heard that correlation doesn't imply causation. So we're looking at associations between variables that indicate whether or not values go together. But it doesn't necessarily suggest, if you have a significant correlation, that changes in one variable cause changes in the other. It doesn't prove that there's causality between those variables. And on this point, Thomas Sowell, who's an economist, remarked that one of the first things taught in introductory statistics textbooks is that correlation is not causation. It's also one of the first things forgotten. And we'll go into why, because it's very, very tempting to make causal claims from correlational data. We have a tendency to see patterns in data and to infer causation in those patterns. So for example, let's say that variable X correlates with variable Y. So they tend to go together, An increase in X tends to result in an increase in Y. But what kinds of explanations do we have available to us to explain this relationship? Why do these two things tend to go together? Why are we seeing this relationship? And this is where causation comes in. And there are a few different causal explanations for correlational data. So for instance, X might be causing Y. We have a direct causal relationship between the two variables. Or alternatively, Y might be causing X. So also a direct causal relationship, but in the opposite direction. Or we might have a situation where X is causing Y and Y is causing X. So we have a bidirectional causal relationship. Or we might have a situation where X and Y are correlated with one another, but they don't cause each other. They might be, for instance, consequences of a common cause, a third variable, variable Z in this case. Another explanation is that X and Y both cause Z, this third variable. Or of course, another explanation is that X and Y both cause Z, that they're correlated with one another because they have this causal relationship with this third variable. And of course, another possibility is that X causes Z, this third variable, which causes Y. So we have this indirect causal relationship. X and Y are correlated, but they don't necessarily have a direct causal relationship with one another. Right, so you can see how there are multiple different interpretations and explanations for correlational data. But let's take a look at a couple of examples. Take the French paradox, for example. So this is where diets that are high in saturated fats tend to correlate with higher rates of heart disease, but not for the French. So their diet has one of the highest saturated fat indexes, and yet they have one of the lowest rates of heart disease. Why? So this sort of seeming paradox led to claims that their high intake of red wine is good for your health, that drinking red wine and eating cheese prevents heart disease. Right, so we have this really interesting example where people automatically jump to a causal explanation of correlational data, that it must be red wine and cheese or some aspects of the French diet that are causing their lower rates of heart disease relative to other sorts of diets. So we see this sort of thing a lot in the news, where we have these causal claims and causal explanations given for correlational data. So red wine has been attributed to helping us live longer and helping us lose weight. This is one that was on the Better Homes and Gardens website. The studies in question, this is referring to a 2010 Harvard study that found that women who drank wine tended to lose weight more than non-drinkers. And so the headline reads, "Science finds drinking wine at night can help you lose weight." That is a sort of causal claim. But when you dig a little bit deeper and read about the sort of research that this sort of claim is based on, we find that it's a correlation that they're using to justify that claim. The studies in question analysed 20,000 women over the course of 13 years and found that women who drank 2 glasses of wine per day, one in the evening, were 70% more likely to lose weight than those who didn't have a glass of wine. Right, so we have this correlation between drinking red wine and weight loss. These two things tend to go together, but it doesn't necessarily mean that one causes the other. We have to be very careful about the sorts of causal claims we make based on correlational data. But there may be other explanations at play here. It may be that the association has nothing to do with alcohol consumption, but rather with things that go along with drinking wine. So people who drink wine may simply socialize more, for example, which comes with health benefits. And they may not have illnesses that would discourage drinking, as another potential example. These are all possible explanations for the link between weight loss and alcohol consumption. So one of the reasons why it can be really tricky to draw causal inferences based on correlational data is what's referred to as the third variable problem. Like there could be any number of other variables, unobserved variables, that are lurking in the background that could explain the relationship that we're observing. So this is a common confound in correlational studies, where we have another lurking or unobserved variable that can explain the relationship between the observed variables. For example, socializing could be a lurking variable associated with more exercise. More exercise might lower the risk of heart disease, increase the chance of weight loss. These are alternative explanations for the correlation we see between those two variables. So whenever we find ourselves drawing causal inferences based on correlational data, we need to be wary of the third variable problem. There are quite possibly other plausible explanations for the relationship, besides X causing Y or Y causing X. So let's make this problem a little bit more concrete with our example. We've observed this relationship between wine and weight loss. So these are things we've observed and measured. But we have this third variable, this lurking variable, which is socializing, the amount of time people spend socializing, which happens to have a causal relationship with drinking wine. And the amount of time we spend socializing is also correlated with other healthy behaviors, like exercising, for instance. And that variable, which is associated with our third variable or our lurking variable, happens to have a causal relationship with weight loss. Right, so you can see how the causal story can be much more complicated and complex than at first glance. And so there are many often unknown third variables associated with the thing we're interested in predicting in psychological research. We might be interested in how sugar consumption correlates with heart disease, or how smoking correlates with lung disease, or alcohol with liver disease, or how taking a particular medication or drug predicts or correlates recovery time, or how we study, how much time we spend studying correlates with our grades, or particular personality variables correlate with our grades, or our income, or how genes, genetic factors and variables correlate with multiple life outcomes, and on and on. These are all examples where we'd like to draw causal inferences. It'd be nice to know whether spending more time studying results in better grades, whether it affects or causes better grades. But we also need to consider whether or not there are other potential explanations for the relationship that we haven't thought of. If all we have access to is observational data about the relationship between different variables. Let's take a silly example. On the face of it, ice cream would seem to be quite the mischievous treat. As ice cream sales increase, obesity, crime rates, drownings, and forest fires also tend to increase. So does this mean that there's something in the ice cream causing people to commit crimes? I think we can probably safely say that it's not causing these things, and yet the correlation exists. So simply knowing that a relationship exists between two variables doesn't tell us anything about whether one variable is causally affecting the other, or in which direction the causal arrow flows. It could be that crime works up an appetite, for instance, or in this case, soaring temperatures could be a lurking third variable that provides a more believable interpretation of the relationship. People are more likely to eat ice cream when it gets hot, for example. And heat is also linked with increased crime rates. But again, we can only really describe the relationship. We can say that these things tend to go together, but we can't say that they necessarily cause each other. To do that, we need to run a randomized controlled experiment. So these are really the best way to identify and establish causal relationships. And this is because as experimenters, we have control over the independent variables. We can wiggle and manipulate them. We can randomly assign participants and materials to different conditions. And we can help manage other sources of error. Think back to how you used to find things out when you were younger. When you did science experiments in school, where we wiggle one thing at a time and keep everything else constant. to see what effect light has on photosynthesis in plants. Or I remember having one of those grass heads where you've got a bit of soil in a stocking with beady eyes on it. And we experimented on keeping our grass heads by the window or tucked away in the classroom to see whose grass heads would grow the fastest. So experimentation is the best way to establish a causal relationship. It allows us to say things or claim things like X affects Y, X decreases Y, improves Y, increases Y, causes Y, results in Y, benefits Y, is bad for Y, hurts Y, changes Y, is good for Y, right? So in each of these expressions, you have an independent variable, X, that's affecting or impacting or causing a change in your dependent variable, Y. So remember, your independent variable is the thing that you manipulate and change, and your dependent variable is the thing that you measure. It's the thing that you affect in experimental speak. But of course, it's not always possible to run an experiment, and indeed ethical to do so. And so sometimes correlational data, observational data is the best source of evidence we have for establishing a causal narrative. So what's the big deal about this distinction between correlation and causation anyway? For example, if you observe that as one variable increases, the other one also tends to increase, isn't that good enough? After all, you've quantified and described the relationship, and you've learned something about how they behave together. If you're only predicting events, and you're not necessarily trying to find out how or why something happened, or you're not necessarily trying to alter outcomes, then correlation is perfectly fine. For example, ice cream sales also tend to correlate with the number of shark attacks. And if you just need to predict the number of shark attacks, then ice cream sales might actually be a really good thing to measure, even though it's not causing the number of shark attacks. But if you want to reduce the number of shark attacks, then we need to find something that genuinely produces a change in the number of attacks. And there do tend to be many situations where we do want to affect the outcome. So for instance, we might want to improve our health by exercising and going to the gym, or using a particular medication, or taking the flu vaccine. We might want to improve outcomes, like changing up our study behaviors to improve our performance on exams and assessment at university. So to make intentional changes to one variable to affect our dependent variable, there must be a causal relationship between our independent variable and our dependent variable. After all, if a change in our study behaviors doesn't result in an improvement in learning, then what's the point in making the change? If medicine doesn't cause an improvement in our health or ward off disease, then what's the point in taking it? So on the topic of correlation and causation, see if you can spot a few examples of this in the news, where it seems as though overly causal claims or explanations are being made or attributed to correlational data. So we've talked a lot about establishing correlations and relationships among variables, about how things tend to go together. But how do we find out whether or not there is a meaningful relationship between the variables that we're interested in? How do we measure relationships in psychology? A bit of revision, but these are still really handy tools to have at your fingertips. So if we're interested in determining whether or not there's a meaningful relationship between two variables, what do? How do we quantify relationships in psychology statistically? So there tends to be two common ways of quantifying relationships in psychology, or computing correlations in psychology. The first is Pearson's correlation coefficient, or Pearson's R. So we might be interested in whether X and Y tend to go together. But with Pearson's R, we make a few assumptions about our data. So for instance, we assume that the residuals are normally distributed, that we're dealing with a linear relationship. So as X goes up, Y goes up by a similar amount, or as X goes down, Y goes down by a similar amount. We're assuming our variables are measured on continuous scales. So temperature would be an example of a continuous scale. We're also assuming that our observations are paired, so that for each observation of X, we also have an observation of Y from the same participant. And we're assuming there are no extreme outliers. Although, as we'll get into a little bit later on, it can be tricky to determine what is an outlier and what isn't, and when we should exclude them and when we shouldn't. But occasionally our data don't necessarily meet all of these assumptions. Then what do we do? What if our data don't follow a linear trend, for instance? Well, another alternative way of computing a correlation in psychology is Spearman's rank correlation coefficient. So we're also making several assumptions about our data here, but it's a little bit more, these assumptions are a little bit more relaxed. So we're not assuming that the residuals are normally distributed. We're assuming that there's a monotonic relationship between the two variables, so such that as X goes up, Y goes up, but it doesn't necessarily have to be by the same amount. Our data can be measured on an ordinal, interval, or continuous scale to compute Pearson's rank correlation coefficient. And we're still assuming that our observations are paired, as we're interested in the relationship between the two variables, and that there are no extreme outliers. So those are the two most common ways of computing correlations. And so Pearson's correlation coefficient would be most appropriate when we're dealing with data that follow a linear trend. So it can be positive or negative, but we're assuming that relationship is linear. So how do we compute these statistics? Well, R has a really handy function called correlation test that we can use. So I've drawn up a few examples here for you to follow along with at home. The first two lines of code in each of these examples is drawing a random sample of 100 values that are between 1 and 5, and with replacement. So if the first value happens to be a 1, then the 1 goes back in the bag to be drawn out again. And I've drawn a random sample of 100 values for X that make up our X variable, and another random sample of 100 values that make up our Y variable. And then we can see whether or not there is a correlation between those two random samples of values between 1 and 5, which is what the third line of code is doing. So you can see I've specified Pearson as a method in the top code chunk, and Spearman as a method in the bottom code chunk. So here I've just simulated some data to serve as the values for our X variable and our Y variable. And we want to know whether or not those the values in those two variables are correlated. And we can also use standard spreadsheeting software as well for computing correlations among variables. So we have our values for our X and Y variables, and we can use the correlation function to select the values of those variables and compute our Pearson's R, correlation coefficient. Now this is Apple's numbers, but it's pretty much identical in Excel as well. So another example for you to try out. But what if we want to go beyond quantifying relationships and establishing whether or not there's a relationship between X and Y? What if we want to know if X predicts Y? If we want to make an inference about the predictive value of our variables? This is where regression comes in. So in simple linear regression, big R squared is identical mathematically to Pearson's little r squared, where we have one X variable and one Y variable. And we make similar assumptions, so that the residuals are normally distributed, that the relationship that we're dealing with is linear, that there's equal variances across the residuals of our two variables, and that there are no extreme outliers. So that's simple linear regression. But what if we have a scenario where we have more than one X variable and one Y variable? And we want to know whether our multiple X variables account for more of the variance of Y. So we make several assumptions here as well, that the residuals are normally distributed, that the relationships among our variables are linear, that we have equal variances across the residuals of each of our variables, that our X variables or predictor variables in correlational research are independent, and that we have no extreme outliers. So again, R makes pretty quick work at computing these statistics for us. There are a couple of examples here for you to try at home with RStudio. The first few lines are randomly sampling 100 values between the range of 1 and 10, and assigning those to each of our variables. And then we're using the LM function in R to specify our model and test our regression model. But because we're sampling random data with these examples, I'd be very surprised if a few significant relationships propped up. It's just a really good way of getting familiar with the sorts of functions that we use to compute these statistics. We'll be focusing on experimental research and statistics from here on out, so we won't be going into correlational statistics in any more detail than this. But the main point to take away is that a statistically significant relationship between variables doesn't signify causation. And why is this the case? Well, there's another explanation that we haven't dealt with yet as to why we might see a correlation between two variables. And that's that they're not correlated at all. They just look like they do. We might be dealing with a spurious or chance correlation. So hypothesis tests, like the ones we just ran through, are inferential procedures. They allow us to use relatively small samples of data to draw conclusions about entire bigger populations of data. So when we see a relationship in the sample of data, whether it's a correlation coefficient, a difference between group means, or a regression coefficient, hypothesis tests help us to determine whether our sample provides sufficient evidence to conclude that the relationship exists more broadly in the larger population. So we can see it in our sample, but we need to know whether or not it exists more broadly in the population. It's possible that random error or luck of the draw produce the relationship we're seeing in our sample of data. So statistical significance indicates that we have sufficient evidence to conclude that the relationship we've observed in our sample also exists in the population. That's it. It doesn't help us establish causation. So there tends to be two kinds of explanations of the variation we see in our data, or the patterns we see in our data in psychology. The first is that we're looking at genuine pattern. The variation we see, the covariation we see between our variables of interest is a result of systematic factors. The second is that variation only looks systematic, but it's actually the result of sampling error or chance variation in the values of our different variables. So this is a neat demonstration of chance by one of my colleagues, Matt Crump. So each of these plots is actually representing purely random data. So each of these plots represents a random sample of purely random observations. There's nothing systematic going on here whatsoever. And yet we can see, especially with small samples of data, that it can look like there's a fairly strong relationship between those two variables, even though we know there's nothing going on. But the problem is we tend to suffer from apophenia. That is, we tend to see patterns or relationships or differences even in random data. And we saw a few examples of this last week. So for instance, people were hearing illusory messages in rock music when it was played backwards. But we see this in more broadly in a range of different contexts. So you've probably experienced pareidolia, which is our tendency to see sort of faces in inanimate objects. We're so familiar with seeing faces that we overgeneralize that to everything that looks sort of like a face but isn't a face. So we're pattern recognizing machines. And because of this, Apple actually reconfigured their shuffle feature so that it would sample songs less randomly, so it would appear more random to people. And as we learned last week, researchers are human too, and are also not immune to sort of over-interpreting data. Examples of irreproducibility in psychology could very well be diagnostic of our tendency to err towards systematic explanations for data, even when chance explanations might be more appropriate. So lastly, I want to introduce you to signal detection theory. So this is a framework for understanding hypothesis testing in psychology. When I first encountered this, it really changed my perspective on things. I started to see everything through the lens of signal detection. It gave me a new way of understanding not just how inferences are made in psychology, but also how we make inferences and decisions in everyday life. So I hope I can pass on a similar inside experience. So signal detection theory is used to measure the way we make decisions under conditions of uncertainty. It was originally used by psychophysicists to measure how we distinguish weak visual and auditory signals from a noisy background. Think actual signal operators. But it's now a more general approach to representing detection and decision problems, and it can be applied in a range of contexts. So here we have the classic way of representing data with signal detection. We have a 2x2 contingency table up in the top left there with 4 different cells. So these contain hits, false alarms, misses, and correct rejections. We have reality on the top, so the signal is either present in reality or it's not. And then we have the human decision on the left. So the human either says that there's signal present or that there's no signal present. Right? So we have 2 different ways of being right. We can say that the signal is present when it is, or we can say that the signal is absent when it is. And we also have 2 different ways of being wrong. So we can say that the signal is absent when it's present. So a miss, we've missed that the signal is present. And we can say that the signal is present when it's actually absent, which is a false alarm or a false positive. Now, notice that we can represent the accuracy or the sensitivity of our experiments or our studies in psychology using exactly the same framework, using the same 2x2 table. So the effect is present in reality or not. And there's 2 ways for us to be right, and 2 ways for us to be wrong. So we can correctly reject the null hypothesis that the relationship or the difference between groups that we've observed is just due to chance. So we're inferring that the effect exists in reality. Or we can also correctly retain the null hypothesis that the relationship or the difference between groups is just due to chance variation. We're retaining the chance explanation for our data. So that's your hits and your correct rejections. But then we also have 2 ways of being wrong. We can incorrectly reject the null hypothesis and make an inference that the relationship or the effect we've observed is due to systematic factors, which is called a type 1 error, which is equivalent to a false alarm. Or we can incorrectly retain the null hypothesis and assume that the sample that we've drawn, the relationship we've observed or the effect we've observed is just due to chance variation, when in fact there is a systematic relationship there. This is a type 2 error or a miss. Right? So rejecting the null hypothesis means that we're concluding that our sample, that the data we've observed are different enough from what we would expect by chance that we're willing to make an inference that there are systematic factors at play. And retaining the null hypothesis means we're assuming the chance explanation of our data, that the relationship or variation we see in our sample is just due to chance or random variation or error variance in our sample. So the important thing to take home here is that rejecting the null hypothesis or finding a significant result in hypothesis testing terms doesn't mean that the effect or the relationship actually exists in reality. It could be a spurious effect or a spurious correlation. There's still a chance that the data we've observed are due to chance. And in this case, we've made a type 1 error, or in signal detection terms, a false alarm. Likewise, if we retain the null hypothesis and assume the chance explanation for our data, it doesn't mean that the effect or the relationship or the pattern of results doesn't exist in reality. It may be the case that we've just failed to detect it. That is, we may have made a type 2 error, or in signal detection speak, we may have missed the effect when it's there in reality. Right? So let's unpack this a little more with a slightly different representation. Here we have two different probability distributions. The blue distribution represents chance variation, or noise. The yellow distribution represents systematic variation, or signal. And the distributions are the natural state of things. So the noise distribution on the left is anything that affects your evidence that you aren't interested in. It might be that participants were interrupted with a text message as they were doing a study, or the instructions were vague and they were misinterpreted, or they blinked and missed the target in attentional and cognitive research, or maybe they misinterpreted the response scale on your survey questions. So these random or chance factors are often independent of one another. Right? So as we measure things in research, we're drawing a sample of data from a broader population distribution. And as researchers, we're trying to figure out whether or not that population distribution is the blue or noise distribution here, or whether it's a signal systematic distribution here. Right? So we're drawing inferences about which one of these distributions we're sampling from as we do research. We're trying to decide whether the pattern of results we've observed is due to chance, so the chance explanation on the left, or if it's due to systematic variation, or the signal distribution on the right. Right? And the line down the middle is our decision criterion. So if our sample of data that we've drawn from a larger population falls to the right of that decision criterion, then we reject the null hypothesis and we infer that there's something systematic going on. But if our sample of data falls to the left of that decision criterion, we retain the null hypothesis. We assume that it's a result of chance variation. And typically in psychology, that criterion is set at p is less than 0.05. We're covering the logic of null hypothesis significance testing in far greater detail in the coming weeks. But for now, you can kind of think about that threshold as our decision criterion in the context of signal detection. So in this representation, if the signal is present, so there is a genuine relationship or effect in our research, and we correctly reject the null hypothesis, then that would be a hit in signal detection terms. On the other hand, if the signal isn't present, that is, our sample of data is drawn from a completely random distribution, population distribution of data, and we correctly say that we're going to retain the null hypothesis, that we're assuming the data are due to chance factors, then that would be a correct rejection. But if our data are due to random or chance factors and we incorrectly reject the null hypothesis, then this would be a false alarm or a type 1 error in hypothesis testing language. And if there is a genuine relationship or effect in reality, but we incorrectly retain the null hypothesis, then that would be a miss or a type 2 error in hypothesis testing language. And those distributions can also vary in various different ways as well. So we can vary, for instance, the degree of overlap between the noise and the signal distribution. That is, getting better evidence changes the degree of overlap. If we have a better measurement, it's easier to distinguish between chance and systematic factors in our experiments and in our studies. So if we've designed the perfect experiment and we've controlled for all chance factors we could possibly think of, then the noise and the signal distributions are going to be further apart. They're not going to overlap as much. Right? So the further these distributions are apart, the more sensitive our experiment or our study to detecting an effect. And the sorts of things that influence sensitivity are things like the robustness and sensitivity of our measures, and the specificity of how we've operationalized our variables, or the manipulations we include, the controls we include in our experimental designs. All of these things serve to tease apart these signal and noise distributions. It makes it easier for us to find an effect, if there is indeed an effect out there in the world. But of course, a lot of the time, it's not possible to have a really precise or accurate measure of the variables we're interested in, particularly in psychology, where the concepts we're dealing with are really quite fuzzy and difficult to operationalize on a continuous scale. So in these cases where our measures are vague or fuzzy, or we haven't quite controlled for random variables in our experiment, we're much more likely to make a type 1 error or a type 2 error. The sample of observations we draw from the population distribution is much more likely to include error variance that could be explaining the pattern of results that we're observing. So this is a sort of critical element of experimental design. Every decision we make is towards teasing apart these two distributions. Okay, so if we can't really control our measurement in some cases, what do? How can we mitigate error in experimental research and correlational research in psychology? Well, another thing we can do is vary the response bias or the decision criterion in this case. So for instance, if we were to shift our response criterion to the left, where we tend to err on the side of making fewer type 2 errors or miss errors at the expense of false alarms or type 1 errors, then we see that we get a really large number of hits, but also a really large number of false alarms. And we call this sort of response bias in research a liberal response bias, where we're tending to err on the side of saying or drawing a conclusion that an effect really does exist or a relationship really does exist in reality, even when it doesn't. So at the expense of making more false positive errors. But what happens if we shift our response bias or our decision criterion the other way? So here, we're erring on the side of making fewer false alarm errors or type 1 errors, where we say that a relationship or a pattern of results exists in reality when it doesn't, at the expense of making more miss errors, where we could be inferring that systematic factors are at play, but we're missing those systematic factors. We're not detecting the signal as easily and as often with this sort of response bias. So notice what this does to the kinds of decision outcomes we have as we shift our response bias around. When we adopt a conservative response bias, which is ideally what we'd like to do in research, where we're mitigating those type 1 errors, or false alarm errors, where we say that a pattern of results exists in reality when it doesn't. But we get a rather large number of correct rejections. But this conservatism comes at a cost. There's a trade-off with any shift in our response bias or our decision criterion. So in this case, in order to mitigate a few type 1 errors, we see we're making many more miss errors, where we could be attributing or inferring that there are systematic factors at play in reality, but we're missing them. We're not detecting that signal. And on the upside, we also make many more correct rejections. So fewer hits and false alarms, but more misses and correct rejections when we have a conservative response bias. So this is an aspect of research that we as researchers have control over. We can choose to set our criterion more liberally or more conservatively. And conventions like p is less than 0.05 in hypothesis testing are reflecting the community's response bias towards making these different kinds of errors. Errors are inevitable in research, but we can minimize them and mitigate them by making smart decisions about how we design our study, how we measure our variables, and where we set the criterion depending on what kind of error we'd like to make the least. So that's response bias. What else can we vary with signal detection? So we also have the base rates or the size of the distributions. But in most experiments, we actually normalize the amount of data we get in different conditions. So we have an equal number of observations per condition or per group. So here we're really using signal detection as a framework or a metaphor for thinking about how we detect relationships and effects in research, but also how we detect structure in our everyday lives. So take, for example, the case of baggage screeners. They have a really interesting and difficult signal detection task where they have to be vigilant and on the lookout for concealed weapons among many bags that don't have concealed weapons. So this is an interesting example where the base rates are quite different between the noise and the signal distribution. So in the baggage case example, there are quite a few bags that don't contain any signal, that don't contain any concealed weapons. So in this case, we have a large noise distribution. The number of observations, or bags in this case, is much bigger in the noise distribution than it is in the signal or the systematic distribution. But in other scenarios, it's the other way around. You can have a small amount of noise or a large amount of noise. And we can also vary the spread of these signal and noise distributions as well, or the variance of the curves. So this just represents how variable our curves are, or how different the things are that make up the curves. So we can have a signal curve that's highly variable, and we can have a noise curve that's highly variable. And so those are the four things that we can manipulate in signal detection problems. So if you remember, we have the extent to which the two noise and signal distributions are overlapping, and that particular element is really important for thinking about the sensitivity or the accuracy or the statistical power of our studies in detecting patterns in psychological research. We also have our response bias, our response criterion, if you remember. So we can set our response criterion really liberally, where we try and mitigate miss errors, but at the expense of making false alarm errors. We can make a more conservative response bias, where we're trying to mitigate those false alarms, where we tend to say that there's pattern when there's none, but at the expense of making more miss errors in research. And then we have these other elements of the signal detection space as well. So we can vary the number of observations or samples of data in the noise and the signal distribution, and also how much those two distributions vary. Okay, so let's try on a few examples of how we can apply signal detection theory. What does this framework really look like when we put it into practice with a few decision problems that we might encounter in our everyday life? So take, for example, the problem of distinguishing real and fake news articles online. So we have our noise distribution in this case would be articles or information online that contains misinformation or disinformation. And our systematic or signal distribution would be the information that we're consuming that contains truthful information. So this is a classic signal detection problem. We probably don't know sort of how overlapping the two curves are, although there's a bit of research coming out now that shows that people are pretty terrible at distinguishing misinformation in online environments. And so I would imagine those two curves might be overlapping. But see if you can sort of put your finger on these different elements of the signal detection space with this real and fake news example. What's a hit in this particular context? Or a false alarm? Or a miss? Or a correct rejection? Where would you set your response bias? Would you prefer to be more liberal in detecting fake news at the expense of making more false alarms, or would you prefer to be more conservative, where you're more hesitant to call a piece of information sort of false or misleading, but at the expense of being fooled by the information that you're encountering? Where along the continuum would you set your response bias? Let's take another example from clinical psychology. Imagine if you're faced with the problem of diagnosing a patient with major depression. Now again, we can conceptualize this as a signal detection decision problem, where we have our noise distribution. So that would be the number of patients, population of patients that don't have major depression, but that present with similar symptoms. And we have our signal distribution, or our systematic distribution. So that would be the population of patients that present with similar symptoms and actually do have major depression, meet the criteria for major depression. And as with sort of all decision and tasks, there's the potential for errors to crop up. So what would a false alarm be in this context, or a miss, a hit and a correct rejection? Again, where would you set your response bias as a clinician? Would you rather err on the side of diagnosing people with major depression in order to mitigate missing patients who genuinely meet the criteria for major depression? Or would you err on the side of being more conservative as a clinician? So erring on the side of not diagnosing patients, but at the expense of making more miss errors. So in this example, I think we start to see that where we set our response bias, or our decision criterion when we're making decisions, is not so straightforward. It depends on the context and very much on what we value and what kinds of errors we'd prefer not to make over the other kind of error. But there are always trade-offs to be made when we're making decisions under uncertainty. And so coming back to thinking about signal detection in the context of hypothesis testing in psychological research, now you know about these different levers you have when you're designing an experiment or testing a hypothesis. Where would you set your response bias? Is p less than 0.05 a reasonable threshold? We'll be spending a bit of time on pulling apart the logic of null hypothesis significance testing in the next few weeks, with a critical eye on why and how we make these sorts of decisions. And so I'll have a bit of time to chat about these things along the way. But the overall take-home message here is that there's a whole lot of uncertainty in psychological research. A significant result doesn't necessarily mean that there is a genuine effect or relationship out there in the world. And likewise, a non-significant result doesn't necessarily mean that there isn't a relationship out there in the world. We can make different kinds of errors. And so research, and good research, is about making design decisions and statistical analysis decisions that mitigate those errors. And that sort of pull on these different levers that we have as researchers in detecting genuine pattern and genuine signal in the world. Yes, we tend to see pattern even in randomness, and researchers aren't immune to this, but there are steps we can take and methods we can use to mitigate those sorts of errors. So what are the sorts of things we can do to help pull apart those overlapping distributions? So I'd be really interested to hear about your examples of signal detection problems that you deal with in your everyday life. So for instance, what would a hit be in the context of your signal detection problem, or a miss, a false alarm, or a correct rejection in the context of your example? Are you more liberal or conservative in your decision making? Right? So have a think about the kinds of decision problems you deal with every day, choosing between products at the supermarket, or deciding on a restaurant to dine at, who to date, whether the leftovers in the fridge are safe to eat or not, and on and on. So we can take a look at each of these problems through the lens of a signal detection framework. So I'd encourage you to give it a go, even if it's informally having a conversation with your friends and family about the sorts of decisions that they make, and whether or not they can identify hits and false alarms, and which ones they'd prefer not to make or not. Okay, so that's a brief overview of signal detection theory, really as a metaphor for thinking about null hypothesis significance testing as a detection problem, and as a broader framework for thinking about making decisions under conditions of uncertainty. And that's the end of our episode. So I'm looking forward to continuing these conversations with everyone in class. So I'll see you then.